Yeah, like if you give us like
Okay.
percent.
Well, let's do problem 1 first, and then we can look at that other. Okay. Let's see. Is this? Close enough. Okay. So let's go ahead and start with problem 1. So problem 1 is supposed to be review from the first 2 weeks of class. And this is where we learned about some of our unit conversions, but we haven't done them in a while, so I thought it was a good idea to do it again. So what's one of those problems?
100 milliliters of 0.125 NaOH.
So we have to remember a couple things. If I have a volume and a molarity, how do I get a number of moles?
Molarity is just moles over liters.
So I can convert this to 0.1 liters. I can multiply those two together. That's going to give me 0.0125 moles NaOH. Now it doesn't want my moles of sodium hydroxide, it just wants my moles of sodium ions in solution, correct?
Mm-hmm.
So I have to look at this and I have to say for every mole of sodium hydroxide, there's 1 mole sodium, 1 mole oxygen, 1 mole hydrogen. Or 1 mole sodium, 1 mole hydroxide. So I can look at this and I can say 0.0125 moles NaOH, 1 mole Na plus for every 1 mole NaOH. That allows me to say how many moles of sodium ions are in solution.
The second one is asking for I think that's barium chloride.
Mm-hmm.
But it has 2Cl, so if you were trying to find the moles of chlorine, would you multiply that by 2?
Yes, you would. Does that make sense? Do you need to see another one?
No, I think that makes sense.
Okay. Let me see. How well is my camera lined up? Not very. So that is problem 1. There's a couple others to problem 1 that are all kind of in the same vein. They're all asking us to look at stuff from 6 weeks ago, 7 weeks ago. We are in week 8. We are at the end of week 8. We got 2 more weeks and then it's finals week. Whoa. Don't worry, for the last 2 weeks all we're doing is stoichiometry.
Yeah.
We're just doing extensive reactions. It's very mathematical and you all feel much better about it. Right now we're dealing with concepts. So earlier, I think before the video started, the question was, are we going to have those empirical formula percent composition questions on this midterm? Unfortunately, no. Now, I think you can completely do those, but because I haven't had a chance to do examples in class yet, I don't feel like it's a good idea for me to put them on the midterm. But I think you can totally do them because they are actually just unit analysis. There are a few logical steps at the end, though, and that's the part that makes me want to make sure we talk about it more beforehand, before I test you on it.
Okay.
Just those logical steps at the end, but it's mostly unit analysis.
Can we talk about orbital hybridization? So,
Sure.
Like,
Okay. Orbital hybridization. So first off, I want you to remember that orbital hybridization is one of those things. I think, where did I have that question? I think it was on a worksheet or something like that.
It was like last week's homework.
Well, no, there's a question that was, if hybrid orbitals are wrong, why do we use them?
Yeah. Oh yeah, that was on a worksheet.
That was on a worksheet. So there's a worksheet question that says, if hybrid orbitals are wrong, why do we use them, right? So I can talk about atomic orbitals, which I'm just going to label AO. That's going to be my S, my PX, my PY, and pretend I can. I'm not even going to try. I'm just going to label it PZ. Actually, I want to change that. Let's do X, Y. Let's call this one Z. right? I'm just going to focus on my S, my PX, my PY, and my PZ for hybrid orbitals. Could we go further and talk about hybrid orbitals with the Ds? Yes, of course, but we're not going to. And these are my atomic orbitals. I'm going to make hybrids in the middle here. And then eventually, really, we should be thinking about molecular. Chem 126, we're not really going to get to it. But essentially, hybrids are a trick. And that question, if hybrid orbitals are wrong, why do we use them? It gets back to the same thing we talked about before I started the video of, well, is it completely wrong?
No.
No, actually, hybrid orbitals get a lot of things right. They get probably, realistically, hybrid orbitals, talking about how I mix these together. So if I'm mixing on a single atom, I'm going to mix these together and I can get an sp, sp2, sp3. If I'm mixing the sp, I would have 2p hybrid, 2p's unhybridized. I have 1p unhybridized, and this one would hybridize all of them, right? Because I've got an s and 3 p's, so whatever I make has to have all of those still taken into account.
So that means 1 sigma bond and 2 pi bonds, or is it the other way around?
Possibly. So if we're looking at the sp, this hybrid is going to form 2 direct overlaps. That's going to be 2 sigma bonds. These p orbitals, these unhybridized p orbitals, would make the pi bonds. So this would have 2 possible pi bonds. This one is going to have 3 sigmas, 1 possible pi. This one's going to have 4 sigmas. So again, the question that I asked on the worksheet was actually a trick question, right? Because it's not that they're wrong; they're mostly right. Right? Realistically, looking at our hybrid orbitals, this gets us probably 80% of the useful information in our atomic geometry, our atomic shape, our orientation of the electron clouds around a nucleus. And compared to getting our molecular orbitals, it's like 60% less work. So we're doing 40% of the work for 80% of the answer.
And so, wasn't there the case though with like the water molecule in the textbook, how the hybridization of the water molecule gave a more accurate description than the valence shell electrons?
Yes, and that's almost always true. The problem is, and we have to be careful about that, right? Because if you look at the hybridization on a water molecule, you're going to get something that's like an sp3 because you've got the 2 lone pairs, you've got the 2 hydrogen-oxygen covalent bonds. In that case, you could say that it's going to be like a 109.5 approximately. But if you actually do a hybridization calculation, you're going to find that it's a little bit less than 109.5. Really, molecular orbital theory is the thing I wish we were doing. But it's like 5 weeks of quantum mechanics, 6 weeks of quantum mechanics before you really understand these. So we'll just say there's an even better answer, but that's where you get to 60% more work to get the last 20% of the answer. Right? Could we do that? Oh, I wish we did. Because almost all of the most interesting things we want to talk about are in that last 20%. At least to me. You go talk to another scientist, you talk to someone else studying a different aspect of chemistry, and they're like, no, all the interesting stuff is here. Like, we can explain almost all of our organic reaction mechanisms and all of that from just orbital hybridization. So this is enough. I'm like, no. I'm like, what about these other things? But that's because what I study is quantum chemistry and molecular orbital theory and those different aspects. So, of course,
So
I'm biased.
compared to the Vesper, which one's more accurate?
Molecular orbital theory is the most correct
Compared
answer.
to hybrids and Vesper.
Hybrids and Vesper actually give approximately the same answer, and that's the real kind of magical thing about hybrid. Magical. That's the real interesting scientific thing about hybrids. This is not magic. It's science. That's the real interesting scientific thing about hybrids. Is the Vesper theory uses this classical idea of, oh, objects are going to push away from each other, and you're going to get some geometry based on this repulsion idea. And then you go, well, no, actually, electrons are quantum objects. They're going to have this weird kind of wave function explanation. However, the wave function explanation gets the same answer. In terms of quantum mechanics, that's like a huge win, right? That's a place where you look at this and you say, oh, quantum mechanics and classical mechanics give us the same answer, approximately. And that's just like, oh, great. They both work. They're both kind of wrong in the same ways as well, though. They both kind of miss. Vesper, hybrids describe more than Vesper does. Hybrids do a better job explaining additional phenomena than Vesper. So, in that case, like, knowing why pi bonds can form or why double bonds and triple bonds form in certain geometries, that's explained through hybrids and having these unhybridized orbitals with the hybrid orbitals. Vesper doesn't explain that.
And so does Vesper and hybrids, do they do an inaccurate job of explaining atoms, or at least bonds with atoms that are extremely large? I remember seeing that in the textbook too.
Yeah.
Discrepancy.
Yeah, pretty much. There's a lot of places where these go wrong, right? So first off, what we have here really only works in the second row, right? We're not including d orbitals, and the fact that, like, the reason that sulfur and phosphorus can break the octet rule. I don't know why I put sulfur and phosphorus in quotes. I meant to put octet in quotes. Why sulfur and phosphorus can break the octet rule. That's what I meant to put in quotes. Sulfur and phosphorus are real things. But the reason sulfur and phosphorus can break the octet rule is because they can also hybridize with the d orbitals, right? And they have that n equals 3. That means they're going to have s, p, and d. So really, hybrid orbital theory does a really good job with carbon, nitrogen, oxygen, which, if you're an organic chemist, is all you really care about. So hybrid orbitals are a godsend in organic chemistry, or they're not. They're scientific. Science again. They're scientists, and it's just like you're really grateful for them because they can explain most of what's going on without having to get into the quantum theory. But when you start going to larger atoms, larger molecules, there's things like, if you look at yttrium, if you look at any of the lanthanides and actinides, they do all kinds of weird, like uranium reactivity is a really, really interesting field of study. And it's just also a really big headache because you have to deal with the Department of Defense, and have weekly, like, materials checks to make sure you're keeping track of uranium to I think it was to the microgram. I worked in a lab that did some of that, and we had to keep track of our material to the microgram. We only had we had less than a milligram, and we still had to keep track of it to the microgram. Which makes sense, given it wasn't even fissile uranium. It was like a non-fissile uranium. But because of its size, because of the f orbitals, because of its electron cloud, there's really weird chemistry you can do that's not completely understood yet. So hybrids give us geometry, give us some information about the bonding mechanisms, and the sigmas and pi's are about the symmetry of the bonds. Sigmas are these like these symmetric bonds that rotate. Pi bonds are these kind of like plate bonds that, you know, if you rotate, they look different depending on how you rotate them. And we get that with hybrid orbitals. We get our linear, trigonal, planar, tetrahedral. We get our Vesper geometries back, and we get a little bit extra explanation.
The pi bonds are the ones on top or in between?
On top and bottom.
Okay.
Yeah. Question here and there.
On worksheet 4, can you talk about number 8?
Before that, anything else about sigma pi hybridization? No. Okay. Let's go to worksheet 4. Worksheet 4, you said number 8?
Yeah.
What is the question on worksheet
It
4?
was a unit cell is determined to be an overlap of FCC anions with BCC cations, which empirical formula would possibly represent the ionic structure.
Cool. I was actually gonna ask about that.
Okay, we need to get empirical formula. What do we know? What do we knew about FCC? What do we know about FCC?
4 atoms per unit cell.
So the fact that it's FCC tells us we need 4 anions. What do we know about BCC?
That's 2 atoms per unit cell.
We're gonna have 2 cations.
Cool.
If I'm looking at this in terms of writing some formula like an MX, or let's just say MAXB, and I want it to be the empirical formula, I'm going to have something that's like a 2 to 4. Now I want empirical, so I'm going to go with the lowest ratio. I'm looking for something that's a 1 to 2 ratio.
Wait, why does it only have 2 cations?
BCC, body-centered cubic. How many atoms per unit cell?
Is that just the one where it's like the one in the center and then
Uh-huh.
the 8's on the corners?
Yeah.
Okay. Okay.
Exactly.
Okay.
So we look at this and we say, okay, I want something that's a 1 to 2 ratio. 1 cation for every 2 anions. And I think that only gives you one choice.
Yeah.
I think it's magnesium chloride.
A cation.
Someone else asked me about this via email, and I was looking at it this morning. I don't have all these memorized.
I
Just
mean,
this question I
There's
looked
only
at.
2 of them that's a 1 to 2 ratio, so
But one of them's like the wrong
Yeah.
order, right?
Yeah.
Yeah.
I just temporarily forgot what it was.
So notice the things that we need to know in terms of definitions here. We need to know FCC and the number of atoms per unit cell. We need to know BCC and the number of atoms per unit cell. And we need to know the difference between anions and cations. Then, in our answer choices, we have to recognize which things are the anions, which things are the cations. I want to point out in this problem, the number of things you're doing for this problem, there's a lot of things that you're doing for this problem, but for a lot of you, you just look at it and go, oh yeah, magnesium chloride, like it's become second nature already. If we gave this to you the first week of the class, it would be nonsense. So I find this problem relatively simple when we break it down a little bit, but it really shows how much we've actually learned in the last 8 weeks. It's a lot. It's a lot. John, did you have a question?
Yes. How do you what's the Lewis structure for nitrogen dioxide?
Nitrogen
Quick question
dioxide.
about that one.
Oh yeah,
Well,
sorry.
So how do you calculate the edge length of that in like
Ooh.
first?
Oh, wait, are you gonna ask about edge length?
Yeah, I could.
Because you asked that on the quiz
Yeah, that was
for
on my-
one that was.
Okay, so let's
Similar.
look at this again. FCC with BCC. I'm gonna go ahead and try to draw this.
Okay. Well,
So, I'm going to draw a cube. I'm going to make an FCC. Faces.
One at the bottom.
There. I just had to make sure I got the one on the front. And then, now the trick is, if it's an FCC BCC overlap, the BCC has to overlap in some way that's offset from the FCC. Otherwise, because we can't have I can't have atoms at the corners of these. So there has to be some like offset. There has to be some way that this fits together. It's either fitting in the spaces in between. I'm not
Oh, because
actually
Can we
sure.
say that like chlorine is
Yeah.
smaller radius, so it like sort of is a little smaller on the inside?
Yeah, so I could imagine, and I would want to. So if I was to give you a problem like this, I would actually give you the unit cell. I would give you some information. I wouldn't just say FCC BCC because there's a lot of different ways. So like if I have a BCC, oh, that's not how you draw things.
Can we be reasonable? Can we assume for the most part that if you ask for edge length, it'll be of a single FCC or BCC, not both? Or
So if we're looking at this thing, I shouldn't have made that one in the middle so big, but I was trying to be dramatic. We'd have to find a way that these two overlap, and then I'd have to give you the unit cell for that, and then ask you to find the angles.
So the picture of the unit cell, is that what you mean?
I would give you the picture of the unit cell.
Okay.
Then you just add up the radiuses.
Yeah,
To get
and
the-
you add up the
whatever size you
radiuses of
want.
the connective lines.
Okay.
This one is this FCC BCC. I'm having trouble thinking of a convenient way that it would overlap. Chances are that this problem was just a theoretical problem, getting you to think about the number of ions. If I really wanted something that was a 2-to-1 ratio, I would probably do. Let's see, this is 2. 1, 2, 3, 4. I would probably do something like a BCC with like something like kind of like the Wurtzite structure. That's not even the Wurtzite structure. Or I would do like an FCC. Oh, I know. Well, that would be a different ratio. There's a couple different options we'd have. So there's like a simple cubic inside of a face-centered cubic. Right, so there's that kind of thing, which as the picture looks terrible because I can't draw 3-dimensionally. If I did the Z diagram for it, it makes a little bit more sense. Let me think. I've got 1, 2, 3, 4, 5 planes. The first and the last are the same. So that's 1, 2, 3 would be this. Something like that. So this is my Z equals 0, 1. My Z equals 1/4. My Z equals 1/2. My Z equals 3/4. So something like this would be a more realistic case where you'd have a 2-to-1 ratio.
And which ones are touching each other in?
So with the way I drew it, it's really hard to see, right? Because if if I drew it in a space-filling way where the atoms filled up all of the space, you wouldn't be able to see through it. I mean, clearly you have to be able to see through it to understand what you're looking at. I'm kidding. This picture is very hard for me to make sense of, even though I made it. Right? It's much easier for me to look at the Z diagram in terms of what I'm trying to represent in 3-dimensional space. These 4 are those 4. These 4 are those 4. But 3D drawing, not my specialty. 2D representations of 3D drawings. I guess really, 2-dimensional representations of 3D, I'd rather do it in a layered fashion. So if I thought about this, the connective layer would be, this one would be touching this one.
Okay.
And then I would say, ooh, this one, there's nothing in the middle for it to touch, so I might bring it back to this one. Right? And so that would be my connective.
Okay.
I would have a triangle through there. And then I'd have to figure out the geometry of that triangle to get the, so that would be like half an edge length. So I'd have to figure out the geometry there to get the half edge length. And that, I think that was the problem that was on the quiz, was something like this.
Right.
It might have been a little bit different. It might have been the Wurtzite structure, which is essentially very similar, except for you erase half of the red dots.
Okay.
And I think the Wurtzite structure is an FCC with this weird like offset diagonal thing. It's got a 1-to-1 ratio, so you see for like zinc oxide and things like. Oh no, a zinc blend. That's not Wurtzite. Zinc blend structure. Wurtzite something else. I know that was a huge. You were all like, "Oh, I think that's zinc blend, not Wurtzite." I know you were all thinking that.
So
But we don't have to know those names. I'll always give you the picture, a better picture than this, maybe even the Z diagram, and ask you to make sense of it.
so this is a 1-to-2 ratio.
This one right now is a 1-to-2 ratio.
And so we know that 2 bonds are coming out of every anion, right?
Well, careful.
Uh-huh.
Remember, because that is in the simple ionic bonding model, but remember we always build up to a crystal lattice.
Right.
So you're going to have multiple things interacting to stabilize those charges.
Okay. And so would we have to be able to determine what the bonds with the other surrounding atoms would look like? Because I'm thinking about NaCl.
Yeah,
And so how,
that would be coordination number.
okay, coordination.
Right? Coordination number gives us that interaction idea, interaction with nearest neighbors. Everyone can come in if we scoot our bags underneath our chairs. Someone can take my chair. I'm not going to be sitting again for a while.
I didn't get back one of those quizzes in class.
Oh.
Is it possible to get that?
Yeah, it's in my pile. Does that answer your question?
It does, and so is the coordination of this type of the same as that? Do those have the same?
No, so
coordination
these
number?
actually, because we've got different ratios, we're going to have different coordination numbers.
Okay.
So if we looked at this guy, we see that it's going to have the 4 touching above it, and we also have to remember it's going to have 4 touching below it. So this thing's going to have a coordination number of 8. If we look at one of these red ones, it's going to have these 2 touching below it, these 2 touching above it, coordination number of 4. But notice the coordination number is a 1-to-2 ratio, just like the number of atoms is a 1-to-2 ratio.
Makes sense.
So the ratios come out
always
the same.
True.
Yeah. Well, for every example that I can think of that I would give you in this class, that would be
And
true.
it's just like whites touching reds versus reds touching whites.
Yeah.
And the whites don't touch each other.
Not in this case, because the way that these are going to
Okay.
kind of push them apart a little bit.
So I have 2 sort of unrelated questions, but
Sure.
the first one is, how do you draw nitrogen dioxide? That was
The
in,
Lewis structure?
yeah, that was in worksheet 4, and I had trouble coming up with something that like made sense.
Let's all try to draw nitrogen dioxide before I put it on the board, since I'm doing something else right now. Two quizzes. That's you, right? Yeah. Cool.
And then the other one is,
So let's finish this question first, and then we can come back to the other one. Write it down if you're like, oh, I'm gonna forget it. But nitrogen dioxide, not nitrite, NO2. Let's draw 2 things. Let's draw nitrogen dioxide and let's draw NO2. Sorry, nitrogen dioxide and nitrate. NO2 and NO2 minus. One of them makes a lot more sense than the other.
Oh.
that's because that's how it wants to be. It wants to be in nitrite because it's more stable.
Kind of. Wants to be is a difficult way to think about it, but essentially, yeah, it's energetically favorable for that nitrogen to take up another electron. Nitrogen has 5 electrons?
Yeah.
Oxygen has 6 electrons. Got 2 of those. So that's going to be 12, 17 electrons. We're already in trouble. Odd numbers of electrons are bad news. 5 electrons, 12 electrons, 1 extra electron, 18 electrons to distribute. That one's going to be a lot easier to deal with. Let's do the easier one first. And we'll talk about why NO2 is strange. So in nitrite, NO2 minus, I'm going to put my least electronegative thing in the center, propose my skeletal structure, double bond to minimize, something like that. Nitrogen follows its typical trend. It's got 3 bonds in a lone pair. This oxygen follows its typical trend. It's got 2 bonds, 2 lone pairs. This oxygen is off. And if we do the formal charge calculation, we're going to get a -1 on that. Formal charge for each thing, that would be a -1, a 0, and a 0. Right? That's gonna be pretty stable. Of course, we could also draw a resonance structure associated with this and say that it's not really a single bond and a double bond, and the electron is not, there's not like charge on one side, but it's symmetric, and the charge is going to be distributed over the molecule as that double bond flips back and forth. We can look at this and say the bond angle is going to be about 120 degrees because it's got 1, 2, 3 things attached, so it's going to be a trigonoplanar geometry. It's going to have approximately 120 degree bond angle, and it's going to be planar. You can say all of that information. From that, we can say, oh, since it's trigonoplanar, this is going to be a polar molecule. The way I have it drawn here doesn't communicate that, but if I draw it with the geometry, clearly I'm going to have an increased concentration of electronegativity at the bottom. The nitrogen is going to be slightly positive. This thing is going to have some dipole moment associated with it. We can get all of that information. Now, the dipole moment, it's funny to talk about, and usually to communicate that the thing is overall negative, we'll put a bracket with a minus there to say this thing has a minus charge someplace on it. Now, it's a little bit funny to talk about something that's got a negative charge, something that's an ion, having a dipole, because the ionic interactions are always going to be stronger than the dipole interactions. Typically, we only care about these strongest interactions. Technically, yes, this has a dipole moment. It's not going to matter that much because the ion interaction is going to be much more important, energetically speaking. Let's go ahead and now do this with NO2. We will propose the same kind of skeletal structure, putting the less electronegative thing besides hydrogen in the middle, bonding our oxygens. And we already know this one's going to be a problem because we've got an odd number of electrons. So I've got to make some choices. I am going to make this choice. Why? Because I know what the answer is supposed to be. Right? What are some other choices we could make? Now, we could say double bond there, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16. But if I put a double bond there, I've got everything with 8s, and I've got one more electron I have to put someplace.
You just place it on top of the nitrogen.
If I do, I'm breaking the octet rule, right? I'm
Right.
filling past the closed shell. I want to make sure that I have my closed shell on nitrogen.
Right.
And right now it's already got 18 electrons occupying those S's and P's. Did I say 18? 8. It's got 8. 8 electrons occupying those S's and P's. So I really can't put another electron on nitrogen. Same thing's true for both the oxygen. So this structure is going to say, well, I've got an extra electron that I need to do. So if I erase that double bond, put a lone pair there, I can put a dot on nitrogen. Now, if I do the formal charge calculation on this, I'm going to do the formal charge calculation on nitrogen. I'm going to have 5 minus 1 minus a half of 6. That's going to be plus 1. Formal charge on oxygen with 1 bond is going to be 6 minus half of 1 minus 1. So formal charges in this case are going to be 0. Sorry, what? No, I just calculated that. Minus 1, plus 1, and 0. Notice overall that's going to give me a neutral charge on the molecule, but I do have this kind of weirdness going on. A couple things we should look at when we see this. We should say, oh, okay, this looks like it would be reactive. Is nitrogen dioxide safe for us to breathe? Definitely not. It's reactive. In fact, nitrogen dioxide will react with another nitrogen dioxide to make dinitrogen tetraoxide, which I think was on your nomenclature quiz.
Yes.
Dinitrogen tetraoxide reacts. So if you go to some place where there's a lot of nitrogen dioxide in the air, I don't know, say Los Angeles, and you increase or decrease the temperature of the air, you're going to convert your nitrogen dioxide into dinitrogen tetraoxide, which is going to have different optical properties. One of them is this really dark, murky brown color, and the other one is pretty much transparent to light. So if you're in an environment where you've got a lot of nitrogen dioxide in the environment, and you're on it's a hot day, that will change which of those compounds exists, nitrogen dioxide versus dinitrogen tetraoxide, and you'll get a really brown sky. Because this thing is reactive. It'll even react with itself. Yeah.
So, for on the worksheet it asked what is its molecular structure, and because it only has one or like a half a lone pair.
But it still has an electron there, which still means there's an orbital that's occupied there.
Okay, but is it like so? But it wouldn't be like just a normal bent. It would that's common 120 degree.
Well, so, and you can argue with me, right? This is where I've always said it's approximate, right? So, 120-ish, probably a lot less than 120, probably a lot more than 120, because that single electron is not going to have as much pushing force, right? So it's probably going to be somewhere, probably like, I don't want to throw out a random number, but it's going to be somewhere between 120 and 180. Probably still closer to the 120 side, because it still needs to have a particular geometry associated with it, but it's not going to be exactly 120.
Will we need to know approximate angles for the midterm?
No, I'll just, I mean, yes, but the only ones that we have are 120, 180, 109.5. Those are the only ones we have for our approximate angles.
For that formal charge calculation, I know this is small. I
Yeah.
think we're missing a 2 for the 1/2 times.
It's just on the times one.
Oh, yeah, yes.
2, right?
2. I sometimes, in my head, just count the bonds, because it's just 1/2 the number of bonding electrons is the number of bonds.
Yeah, it's an easier way to do it.
Okay, and then
The reason we don't do it, one more thing, the reason we don't do it that way is because we like to have the entire calculation in terms of electrons, and not have to think like, oh, it's electrons, bonds, but bonds are electrons. We just keep it all in terms of electrons. Go ahead, yeah.
okay, so for oxidation, the H's can either be minus or plus, right? Depending on like where they are. -1 +1.
The -1 hydride is very uncommon. There's only a few places where it happens, and those are things that are less electronegative than hydrogen. It happens with lithium. It happens with boron. Boron.
What
Lithium and
about methane or something like that?
methane. The hydrogens are probably +1 because carbon is slightly more electronegative than methane. Carbon is slightly more electronegative than hydrogen. They're almost the same. They're pretty much the same. Carbon is slightly more.
So that it would have a +1 in that scenario
Which thing?
for methane
The
and the
hydrogens?
hydrogen.
Yes.
And which one's more common? Hydrogen's having a -1.
Which one do you think?
I think minus would be more.
Minus is more common. It does happen. It makes some of the most reactive materials. Hydride, H-.
Oh, okay.
So lithium trihydride is a very reactive, or is it lithium tetra? I gotta think about that. But lithium and boron are two of the only compounds. Boron trihydride is one of the, and lithium hydride are two of the only places where we see the hydrides and H-. There's some other weird situations.
It gains an electron?
Yeah.
Did we ever?
It's listed in some common ions lists as being possible,
Okay.
but it's pretty uncommon.
In terms of oxidation state, though, I do have it written. Hydrogen is always like +1 in terms of like.
Always in quotes, right?
Yeah,
Always
But in
+1.
for the purposes of this class.
Yeah,
okay.
pretty much every place we run into hydrogen is going to be in that +1
So what would
state.
be the oxidation state of C2H4 of the carbon?
C2H4?
Or not C2H4, let's say C3H8.
We could do C2H4. C3H8? Yeah, we could do C3H8.
Yeah, but what would be the carbon?
So, this gets to the organic compounds and the trick that we didn't do. Let's go ahead and do it for fun.
Half reaction?
What's that?
Is it the half reaction?
No, it's not a half reaction. So there's two ways we can think about it. We can do C2H4, we can do C3H8. Let's do both and talk about the oxidation states of the carbons there. If we do C2H4, first let's write the Lewis structure. C2H4 is going to be something like this. I'm going to have plus 1, plus 2, plus 3, plus 4. The carbons must be minus 2s each. Right? If I have 4 pluses, the carbons must be minus 2 each. Done. That one's easy. C3H8 is a little bit more tricky, and you can already see why. Even odd numbers again, right? So if we look at C3H8, we're going to have carbon, carbon, carbon. And because, and you can kind of see why these are going to have different charges, different oxidation states associated with it. This carbon has 3 hydrogens, this carbon only has 2 hydrogens. Right? So the amount of charge that each one is dealing with is going to be slightly different. So we can think about this in kind of 2 ways. For our class, I'm kind of okay with the idea of average formal charge. The average formal charge on carbon is going to be plus 8 divided by 3, and the negative version of that, right? Because I've got plus 8 for my 8 hydrogens. That's a hydrogen. And the carbons must be the opposite sign of that charge to balance it. So this would be like, can I do this? 2 1/3. Oh wait, math is hard. 6, 7, 8. 2 2/3. Right. So essentially, and if you look at this, each carbon has 2 hydrogens, and then 2 of them have an extra. Right. So we can make sense of it that way. That would be the average formal charge. Really, what we should do is the trick that I didn't teach well because none of you are going on to organic chemistry. Now I've got that on video, and I hope none of my colleagues watch this and are like, you didn't do that? None of you are taking organic chemistry. So the second trick, the way to get the actual oxidation states for each carbon, because it turns out the truth is these 3 carbons are going to have different oxidation states depending on what they're bonded to. So the way that we do this is we essentially say the more electronegative thing is going to take all of the electrons, and if we have equal electronegativities, they're going to split the electrons in a bond. So the hydrogens, being less electronegative than carbon, are all going to end up positive. This carbon is going to take both those electrons, both those electrons, both those electrons. And I'm just going to draw all the hydrogens. The hydrogens all end up in the plus state. This bond between the carbons, the electron gets split between them. Because they have equal electronegativity, they share the electrons evenly. Then I can do essentially a charge on this. Carbon is 4. Starts with 4. It's going to have 2, 4, 6, 7 electrons. That's going to be a minus 3. Carbon is 4. It's got 2, 4, 6 electrons, minus 6. Carbon is minus 2. And this one is 4 minus 7, minus 3. So minus 3, a minus 2, and a minus 3. If I average that together, 2 2/3. I'm not going to ask you to do it this way. I'm okay if you do it this way for this class. What's that? You like this? This makes more sense. This is what's really kind of going on.
That makes more sense.
You can, like, I mean, if I'm being honest with you, I'll try to keep it cases where it's even. So you don't even have to worry about this, like, fractional kind of idea. But yeah, that's really kind of what's going on in terms of the electron sharing. It's a little bit weird to talk about oxidation states in organic compounds to begin with, but this is how we can kind of think about it in terms of oxidation reduction. The thing that makes it weird is now if we did the combustion of C3H8 with O2 and we made CO2 and H2O, you've got carbons that are going to end up in the same oxidation state. They're all going to end up in the +4 state, but they're losing different amounts of electrons to get to that +4 state. So you've got a disproportionation. Well, is that technically disproportionation? I don't think that's technically. So I don't think that's technically disproportionation. So that is when you have one compound that is both oxidized and reduced. In this case, these are all being oxidized, but they're just being oxidized at different amounts.
How do you have one that's oxidized and reduced?
Weird situations. It was going to be hard for me to think of a compound where that happens. It's something that essentially self-reacts. There's some nitrate compounds, there's some nitrogen-containing compounds that do it, but I can't think of a good example off the top of my head.
Photosynthesis maybe, like, and then it was like the CO2 and then the carbon goes down and the oxygen goes up.
I guess, yeah, the reverse of combustion in photosynthesis, not the reverse of combustion, but photosynthesis, the sequestration of carbon dioxide would do that, because your carbons and your oxygens would both be your carbon would be getting reduced and your oxygen would be getting oxidized. In that case, when you produce O2. Yeah, good example. Other questions? Yeah.
So when you have a long chemical name that's clearly like alcohol type, it's like, and then it also has like parentheses 3,3 close parentheses.
Uh-huh.
Are we supposed to be able to convert that crazy word into a structure?
I want to say yes, but I think kind of yes. So I think I would have to give you more clues, essentially, right? So you're thinking of the IMF. Everyone okay with this so far? Good. Okay. So you're thinking about like the IMF lab where you had those crazy long names, right? So let's pick one and see. Like I feel like you should totally be able to, because the naming structure is quite logical and really tells you what's going on. So, for example, 3,3 dimethyl 3,3 dimethyl butanol. The way I learned to name these is a little bit different. I still struggle with the new naming method. I would call this 3,3 dimethyl 2-butanol, but 3,3 dimethyl butanol kind of communicates where the alcohol group is. So let's break this apart. I'm going to have a butane, I'm going to have a methyl, and actually I'm going to have two methyls. So I'm going to make a butane chain first. Monkeys eat plenty of bananas. That's going to be 4 carbons. So I'm going to go carbon, 3, 4 carbons. On the second carbon, I'm going to put an alcohol group. On the third carbon, I'm going to put a methyl group. And then on the third carbon, I'm going to put the other methyl group.
Okay, that's
3, 3, so that's telling us where the two methyls are located. The
Okay.
2 tells us where the alcohols are. And then I'm going to fill in the rest with hydrogens. Make it so I've got everything. If I wanted to do the line drawing with this, which I'm okay with you doing line drawings, I would do 1, 2, 3, 4. I kind of don't
if we
want
wanted to be crazy, can we just like take that whole thing that we just put, like that whole word, and then in front of dimethyl we just put that there, and then it's just gonna be itself on top of that.
Wait, what do you mean?
Or like maybe if we just change the dimethyl to dibutanol, that would make sense.
Dibutanol? So that would be a little ambiguous, because are you saying there are 2 butanes or 2 alcohols? So are you to be clear, you're trying to make a new compound.
Yeah.
Yeah, you're trying to make a new compound. So let's make a new compound. Let's say we wanted 2 alcohol groups. let's do. Forgot something. Butene 1,2 diol. Draw the structure. Very logical, right? Now she wants it. Did you draw this?
There's a picture there if you want to.
Do we have to know the names of all the different like compounds like butane 1,2, or like the different like 1 butanone or like 2 pentanol or whatever?
So, at this point, we should be comfortable with all of the functional groups.
Yeah.
So that if I remember correctly, there are 9. There are the aldehydes, the ketones, the carboxylic acids, the ester, the ether, the alcohol. Well, I lost count. Aldehyde, ketone, carboxylic acid, ester, ether, alcohol, alkane, alkene, alkyne. Carbon single bonds, carbon double bonds, carbon triple bonds. I mostly care about the 7 that have the oxygen-containing functional groups. Yeah.
So in that name, what does the 2 indicate?
The 1,2 communicates the fact that. Oh, sorry, I made the wrong compound.
It should be 1,
This way.
4.
It's on the second.
Yeah.
Wait.
Yeah.
Oh.
Gotcha.
I meant to write 1,4 because 1,2. This would be a much more reactive compound than a 1,4. Right, having those alcohol, having the functional groups close to each other, it is going to be a bit less stable. It's going to be a bit more reactive. I think you could force this thing to exist in a laboratory. I don't know how stable it would be. The 1,4 diol is stable.
Yeah.
Yeah. So that was my mistake. Sorry about that. What I
Um,
did in my head versus what I did on the board.
Just to clarify though, what is the 1, 2 then?
So the one. So recognizing that the diol here is telling me that I have 2 alcohol. Right, so this is carbon 1, this is carbon 2. It's telling me that I've got 1 alcohol there, I've got another alcohol there. It's giving me the locations of those alcohols.
And the butane is just the structure of it.
Yeah, so the butane part tells me that it's a 4-carbon chain.
So for the endings, like OL would be that, and then AL would be aldehyde, and then oic acid would be
The carboxylic,
acid, and then if it ends in 1, it would
which
be
we
the
actually call
ketone.
ONE in
One.
chemistry. ONE.
Oh wow.
We have to like, are we gonna have to like look at a name and then like say what compound it is based upon like, say if you said butan 1 all or something like that, that would just be wouldn't that be a 4-carbon chain with a alcohol in the first one?
Yep. Yeah.
Will we have to do that on the midterm?
I think it would be fair if I had did that.
Okay. But they would be simple ones, right? Not
Yeah.
like, okay.
Not the thing.
I want to put another crazy one up there for us to try.
Can I think of a crazy one off the top of my head?
How do you name them if they have 2 different functional groups?
Yeah, do one of those. After you explain it.
I'm trying to think. I wish Dr. Legani was here because she'd be like, "Oh, I can do all this." So sometimes you get special names for things, depending on the combinations of functional groups. For example, having an amine group, we didn't have to learn the amine group. That's an NH2 group. Having an amine group and a carboxylic acid group in the same compound is a very common thing, but those all have special names. And when you have an amine with an acid, like carboxylic acid in particular, those are amino acids. And they have special names. And when we start getting to these larger compounds that have multiple functional groups, they have pretty specialized names. I'm trying to think of a simple one, but I would, in order to make sure that I don't say something silly on a video, I would want to look up an example rather than just make one up off the top of my head.
Okay.
Yeah, I don't know if you all know this, but it takes me quite a while to make your exams because I make sure that I'm looking up real. Like, you notice on the worksheet, one of the problems we looked at earlier, I was like FCC with BCC. It's not a real thing, so I wouldn't want to put that on an exam. It's fine for like a little kind of like test your thinking concept idea. But for exams, I pretty much always try to make sure that I'm grabbing real things for you to think about, real things for you to consider. Other questions? Yeah.
For like that, how many things like butane do we need to remember?
So I only asked you to remember the methyl, ethyl, propyl, butyl, so the first 4.
Okay.
But there's also the pentane, hexane, heptane, octane for the next 4. Nonane, decane, right? Those Latin prefixes. Greek prefixes or Latin prefixes? I think those are the Greek prefixes.
Does that just mean you have a carbon each time?
Yeah.
Okay.
Right? But like, you know what a pentagram is? It's 5, so pentane is 5 carbons. You know what a hexagram is, right? It's 6, I think. Hexane is 6 carbons. You know what an octagon is? 8 sides. Octane is 8 carbons.
So alkane, alkane, alkyne, just for that vowel sound, just goes down in the alphabet. For 1, 2, 3.
Yep.
Was that on purpose?
I'm pretty sure it was.
Cool.
What if they had a quadruple carbon? So there was no more vowels left. Alkazin.
Also doesn't really happen. And we could explain why that doesn't happen if we look at the orbital hybridization possible on carbon. Right? And what is necessary for a quadruple bond to occur, you need to use your d orbitals.
It doesn't get there.
And carbon doesn't have d orbitals to make a quadruple bond. So we could actually write a really interesting question. It's not, I'm not going to say it's on this midterm, but it'd be really interesting. Say, like, explain why carbon doesn't form a quadruple bond. And you can use hybrid orbital theory, you can use Lewis structures, you can use formal charge. There's all these different ways where you could show that carbon doesn't make a quadruple bond.
So you run out of vowels in the alphabet.
Yeah, no, yeah. Naming conventions don't allow for it because we're out of vowels. Why didn't unless it's an alcoon, then use the U in there.
Alright, thanks, Dr.
Yeah. Other questions?
So I'm just have one question.
Yeah, what's up?
So on the reactions lab, there was one reaction where it didn't seem to like fit one of those 3 typical reactions.
Which reaction was it?
13.
13. What did you notice about reaction 13? Did you do your net ionic?
The net ionic. It was, yeah, I did that and it came out to no reaction. So
There you go. No reaction. Nothing actually happens in that one.
So the type would just be simply no reaction.
No reaction.
I mean, it is metathesis in the terms of things move around, but
Yes, right? And so we have to be careful because there's 2 different ways that we can talk about our types of reactions. We can talk about it in terms of how we're rearranging things, and we can talk about it in terms of the chemical reaction. Now, saying that it's a metathesis reaction is actually not correct in this case, right? We tried to make it a metathesis reaction, but everything canceled, so that doesn't actually happen,
oh, okay.
right? Because when you do the metathesis style reaction, when you do the double displacement, nothing actually happens. So you tried to make it metathesis, but really nothing happens.
Okay.
So another question I had is, of the 3 types of reactions, precipitate, redux, and acid-base, is it possible for one reaction to be considered 2 or more of those?
Yes. It's a little less common, but there are some acid-base reactions that will also have a precipitate form. There's some precipitation reactions where you'll also go through some redox reaction. We can think of examples where we have combinations. I can't think of an example that has all three at once, at least not off the top of my head. But you can have situations like I think acid-base with precipitate is kind of the most common, easy example to make, because there's all kinds of like sulfate things that will precipitate, but you could also have sulfuric acid react with something and then form precipitate.
Alright, and then like would we be asked that on a test if it matches two of them?
Yeah, that'd be fair.
So you would just say it's both acid base and say precipitate?
Yeah.
Alright, and then when it comes to the acid base reactions, I know that's where one hydrogen positive ion is transferred from one compound to another.
Mm-hmm.
So I'm still a little bit confused on like how you actually identify if that's going on.
So, short answer, long answer. Shorter answer is we make predictions based on whether we've got hydroxyl groups or other things that are going to be accepting that H+, and we can kind of predict some of our common things. The long answer is we want to. The long answer is Chem 126. We spent about 3 weeks, about 3 weeks, talking about acid-base reactions.
So like the ones we'd be asked on a test would be pretty obvious they are.
Pretty obvious, strong acid, strong base, or carbonates.
Alright, and like when it comes to an acid-base reaction, are the reactants, are they always in the form of acid and a base, or could they be other types?
Yes, but there are some things that behave like a base that don't look immediately like a base in terms of strong bases, right? Our definition for strong base is it has a hydroxide, not an alcohol, a hydroxide group, an OH minus group, ionically bonded to something. Some common compounds that can behave like a base, carbonates, you've seen behave like a base. That was a special comment I made. Also, if we look at metal oxides, like calcium oxide, magnesium oxide, that O2 minus can also behave like a base and take up the H plus and form H2O.
Okay.
So yeah, the purposes of those two labs, I can't remember which one because I think I turned it in, where we just dropped like metal into hydrochloric acid.
Mm-hmm.
That was an acid base.
Technically, no. If it's just metal, so we did 2 reactions. We did calcium oxide with acid, and we did calcium with water.
Yeah.
The calcium with water is a redox reaction. The calcium oxide with acid is an acid-base reaction. Let's look at those two and explain.
Yeah. Okay. I turned mine in, so I don't have the.
So, and this is I've had a lot of people ask types of reactions questions of like what type of reaction is this, and it always makes me a little sad because I'm like, let's just use a little bit of logic. Let's do process of elimination. Which ones is it obviously not? And then from which ones it's obviously not, we can tell which ones we have to think between. So, one of the ones that we did, and I did this as a demo, was calcium metal plus H2O liquid forms calcium hydroxide plus, sorry, I didn't give myself enough space, H2 gas. And I'll also write the second reaction we want to consider. That is calcium oxide plus HCl aqueous goes to calcium chloride plus H2O liquid.
Oh.
I take it now that I wrote those down, you're like, oh yeah, that's kind of obvious.
Yeah, I can see that now.
Right, so very clearly neither of these are precipitate reactions, right? I'm not forming any solid. You could say, oh, well, you're dissolving a solid, so it's kind of like a solubility reaction, but when we look at this, we notice calcium here is a +2 charge, oxygen here is a -2 charge, hydrogen here is +1, chlorine here is -1. Calcium here is +2 still. Chlorine here is -1 still. Hydrogen here is plus. Oxygen here is -2. Oxidation states have not charged. Oh, sorry, have not changed. Our charge hasn't changed in any of our atoms, so it's not a redox reaction. I've got an acid. I've got water as a product. This looks like an acid-base reaction. Oxides can act like bases reacting with an acid. In this other case, I've got calcium solid, which is a charge of 0, +1 charge, a -2 charge. Calcium here is a +2 charge. Boom, right away I can already tell. So I'm going from a 0 to a +2. Change in oxidation state. That's going to be a redox reaction. Also, H2 gas is produced. That's a 0. Boom. Change in oxidation state. Must be a redox reaction. Yeah.
Does there have to be two things that switch their?
Yes. Right. In a redox reaction, you always need something reduced and something oxidized.
Oh, so
That's
it wouldn't
why.
be balanced anyways, right?
Yeah. Otherwise, you wouldn't have charge balance. The electrons that this thing loses have to go someplace. We can't just have electrons disappearing. They have to go someplace. So we always have a reduction, and that's why we always call it redox, not reduction reactions and oxidation reactions. It's always reduction-oxidation reactions, right? Because they're always together. Similarly, we don't typically talk about acid reactions and base reactions. We talk about acid-base reactions, right? Because you really need something that's going to donate protons and something that's going to accept protons. But I'm getting ahead of myself. That's starting to think about acid-base reactions in terms of the Bronsted-Lowry definition, which you don't do till Chem 126, which unfortunately none of you are taking. It's not too late to change your major. Just saying.
I'll consider it.
Or you can just take it for fun. It's a good class. It's one of my. It's in the Gen Chem series 126 or 129 if you're not a chem major. It's probably my favorite class in the series. It's where you finally get to look at reactions in terms of what's actually happening, how much is happening, and you get into the details. Lots of math. My students that take 129 get lost in the math, and I bet you don't do fine with the math. But there's a lot of math. Other questions? Turning this in now. Oops, sorry.
What was the mnemonic that you used to help remember what's oxidized and what's reduced?
Leo Gur is the one that I like. Loss of electrons is oxidation. Gain of electrons is reduction.
Now, quick question for the ones we had in the lab where we added magnesium metal to hydrochloric acid.
Mm-hmm.
Was that an acid base then? Or no, wait, no, never mind, I got that.
Oh, I have one more question. So for the lab we did on Tuesday, are we finishing that today or on Tuesday? Next Tuesday?
Next Tuesday. I thought the midterm today would be enough to deal with.
Okay.
I thought. I hope.
Alright, and then you said it's due on next Thursday?
I don't think I said that, but I think that's going to be when it's due.
Okay.
Yeah.
Yeah. On worksheet 5, number 9 said a strong acid will putting blank into solution. And I had originally said completely dissolve and put hydrogen ions, but that was wrong. So I was wondering.
Wait, is that wrong? Did I say that one was wrong?
Yeah.
Because you emailed me all your things and was like, which ones did I get right?
Yeah.
Which question was that?
Number 9.
Oh, I must have been off the line. I thought you put let's see, number 9 on worksheet 5.
Yeah. Okay.
I put D. Oh, I thought you put D.
Okay, so B is right. Then.
B is correct. Yeah, I was probably looking at it sideways and just meant because the picture you sent me was sideways, and I probably was looking at answer 8 instead of answer 9.
Okay.
Did you get 8 right then? Yeah. No, you're fine. You got it right. Yeah, that was just me looking at it incorrectly.
And worksheet 4, number 1 is about the ability of metal to conduct heat and electricity.
on worksheet
Is it
5.
what's the difference from ionic lattice energy and the sea of electrons model?
Ooh, so much.
Well, but doesn't the sea of electrons model like have to do with the lattice structure?
Not exactly. Right, so when we're looking at an ionic lattice, we're talking about one thing holding onto electrons next to another thing that's holding less electrons, and the Coulombic attraction between the two. What's the sea of electron model? I mentioned it in class, it's also in the textbook.
So it's just like how electrons flow through the lattice, isn't it?
A particular type of lattice. There were two things we needed for the sea of electrons model to work. So we need to know those things, otherwise it doesn't make sense. We needed d orbitals, so like our transition metals,
Oh, okay.
and we needed similar electronegativities, right? So to make a metallic lattice is different than to make an ionic lattice,
Oh, okay.
right? So you probably, you almost got the right idea, but you kind of just said, oh, all lattices are the same. Metallic lattice and ionic lattice are going to be quite different. That's part of why metallic solids and ionic solids have such vastly different properties. So, like, ionic materials snap and break, metallic materials bend and can be shaped. And you can explain that with the sea of electrons model. Other questions? Since the questions are kind of slowing down, I think I'm going to stop the video. Let me make sure there's nobody asking questions online. Is that right? Who's watching? Oh, somebody is watching. Hi, person watching. If you have any questions, come by office hours or email me.